So I don't have a recording for last class because of another sort of crash, but I have found a different way of recording. So, just if you're using the YouTube material at all, it should be fine now. Okay, anyways, so we're gonna continue from last class talking about approaches to look at multiple discrete outcome variables. So the most common one we've covered is the multinomial logistic. And so we're going to look at a couple of alternatives at the start today before we move on to kind of a different topic area. Any questions about last class? Okay, so we're going to just look at a couple of other classification examples. And the main thing is more to highlight differences in capabilities. I would encourage you, if you're doing classification type problems, MNL is kind of the default that a lot of folks use at the sort of base level, but we'll think about, potentially a couple of other different models that you might use for different purposes. So the first one being, so we'll look at other classification examples. The first one being linear discriminant analysis. So this is also known as LDA. So this is better for well-separated classes compared to the MNL. If your predictors are normally distributed, this will be more stable than a logistic regression. And oftentimes this is a popular option with more than two response classes. Okay. In the MNL, you calibrate to the probability function. That's the piece that we're kind of interested in, and so LDA does that in a pretty different way. I'm going to write the equation, and again, this is just maybe for reference, not something you need to memorize. So Bayes' theorem looks something like this. Where f of x is the density function of x for an observation k. And this is the probability of outcome k. So the reason why this is more stable with normally distributed predictors is because we don't actually know what the density function f of x is. And so what the LDA does is that it assumes this. So f of x is assumed to be in an LDA. Does anyone recognize this equation? Look like anything? Yeah, it's a normal distribution. So the basic idea is that your density functions are just assumed to be normal in an LDA. And so if it's the case with the actual data, this model tends to, let's say, predict better. Okay? A lot of the times, practically speaking, you're going to achieve, I think, similar results with a logistic regression. Just know that some of the properties may lead to sort of better adherence to your results. So for this part, I'm just repeating what we did last time. And as a reminder, what we're looking at is this data from our Disney Plus data set, where we look at how movie ratings kind of correspond to the length of the movie and then the vote rating of the movie, right? And if I run through the LDA, which, I'm not going to have us follow along this time. The code is basically the same. The main thing is that running the model, instead of saying GLM fit, family binomial, we use this LDA function. I need to put the right package. I believe this is in the mass stats package. Yes, okay. So you'll need to put library there first. Okay, and so we use this function LDA to run the model. And if I do kind of the same thing that I did last class, we should see it takes a little time to render. Okay, so we should see again, essentially across our feasible space, which is across the values of our movie runtime and our movie ratings. Again, these are normalized, so LDA requires normalized variables. It'll end up looking something like this. Okay, so very similar to what we were seeing before. And these will have like a corresponding error rate, which we can use as a metric, for example, to compare different types of models to see if one does better than the other. But each of the regions will correspond to what the model is saying has the highest sort of probable outcome for any of our response classes. Okay. Any questions? So that's an example of a model that is similar to a multinomial logistic, and there are specific criteria that you can think about where you're doing this kind of trade-off between models, and those are, as I was mentioning, right, well-separated classes, normally distributed, and if you have more than two classes, oftentimes these kind of point more towards something like an LBA. Okay. Let's look at one more example before we move on. I think this one's maybe a little bit more interesting. So we'll jump back over here. So this one is known as K nearest neighbors. And maybe you've heard of this before, maybe you've even used it before. And let's talk about how this works. I'm going to first write out kind of the math equation. Looks something like this. I didn't actually know there was a formalized equation for this algorithm for a long time, but here we are. Okay, and the way to interpret this, so given a positive integer k and test observation x0, identify the k points closest to x0 represented in the equation by n naught. This will estimate probability for class J as the fraction of points in n naught whose response equals J. And then classify x naught to class with largest probability. Okay, so I'm not sure that this explanation is the best either. This is kind of the formalized definition. So let's do an example. I think this is going to be the most easy to digest. I'm going to draw a little graph here, and we're going to have a couple of points. Looks something like this. And then we'll have something like so. Okay. So I'm going to plop down a point right here. So is this question mark an X or okay, What do you guys think? Raise your hand if you think this question mark should be a blue point. Okay, raise your hand if you think it should be a red point. Okay, we're not so sure, right? So, how does this work? At k equals 1, we classify based on the closest neighbor. Okay, let me actually, I'm gonna do it like this. Okay, so based on the way that I drew it, I think the closest point is this guy here. And so, you know, actually, I'm gonna move this to be a little bit more interesting. We'll do over here. So this point is closest to a blue one. And so when k equals 1, it means only look at the nearest neighbor to you. Okay? So k equals 1, our point is blue. Wait, okay, hang on. I changed my mind. I'm going to move it again. I'm realizing the way that I drew the points. We'll put it over here. Okay, so still the answer is the same. The closest one, let's say, is blue. Let's say we want to now do at k equals 2. Well, in this case, let's say the next closest is this red point. So now you have a red and a blue point. But when that happens, when there's a tie, you go with the one that you were at originally, because that indicates that the original one was a closer point. So this one, in fact, is actually still going to be blue. Okay. At k equals 3, let's say the next closest point is this red dot here. So now I'm closest to 2 red points and 1 blue point. So now the classification changes. And now this is red. Okay? And so as you go on and on, all you're doing is for any particular point in your plot, you are looking at all of the k closest neighbors, and whoever has majority, or the most, I should say, relative to any other class choices, that dictates the class of the point of interest. Okay? Okay, let me ask you guys this. So there's 7, 10, 11. Okay. What would this be at k equals 19? Blue? And why would it be blue? Yeah, there's more blue dots, right? So you could include all the neighbors. You can include all the points if your k is large enough. And in that case, you would get switched into blue. Okay, so even down here, where I'm close to a whole bunch of red dots, if my k is large enough, the prediction will still be blue. Make sense? Yes?
Is this like exclusively a red or blue like result, or is there also like a probability of it being red or blue based on like the relative distance?
The probability is based off of how many dots are in, or the count of dots based on the neighbors that you're looking at. So it is probabilistic, but it's not based off of distance. You could do it like that. There are other models that you could calibrate it in that way. And we'll look at analogs of that in clustering. I guess it's not really classification, but certainly you could if you wanted to. Yeah. Okay. So K is chosen arbitrarily in this example. How would we know what the right K is to pick? Any ideas? Yeah.
Maybe like the total number of points divided by like the number of colors, or like number of colors isn't really the best.
Number of classes, you're saying?
Number of classes. Yeah.
Number of points divided by number of classes. So here this would be like 2, or I mean, so 8.5, I guess. Yeah, I mean, I'm not sure that's going to work out depending on the scaling. So not quite, but you all know the answer to this. Cross-validation, right? So, right, so think about it. I could, let's say I had a couple of test points that I leave out. I'm gonna treat them as like circles and X's, right? Now imagine that I run this model for k equals 1, and then I run it for k equals 2, and then I run it for k equals 3, and I do that all the way to k equals 19. And all I need to do is do my prediction for the location of my new points, and whoever does the best in the cross-validation is the right one to pick, right? Because you're predicting out a sample. It's not the thing that actually calibrates your model. So yeah, cross-validation, same as always. That's an easy way to figure out the right number of Ks. Okay. This very much is the same type of thing where we are balancing kind of overfitting versus not giving enough information to reduce the bias in the model, right? It's kind of the opposite again. So if you're only looking at your nearest neighbor, your one nearest neighbor, you're likely kind of overfitting the model, and then on the other end of the spectrum, you're not introducing enough complexity in the model to overcome the bias. Okay, so any questions about this?
Could you explain again at k equals 3 how it's the red versus the blue?
Oh, it's just the 3 points that are closest to my star. So, okay, let me. Let's do it like this. If I were to go here, that's not a good. Let me see. Where's a good place to do this? Well, probably still. Well, okay. I could do it over here. So here, closest one is blue. Next closest one is blue, and then the next closest one is red, red, red. Probably, right? So on k equals 1, it's blue. K equals 2 is blue. K equals 3 is still blue because there's 2 blue, 1 red. K equals 4 is still blue because you have 2 blue, 2 red. And then at k equals 5, you have 3 red and 2 blue, and then it switches. Does that make sense? Mm-hmm. So it's just about looking at who's closest to you up to whatever your k is.
Okay.
And then whoever has the most is what you are.
Okay.
Yeah.
Just make sure. So the distance is straight line distance.
Straight line distance. Yeah, sorry, I'm drawing like little curves, but yeah, it's just straight line distance. Yeah. Which is really important to think about when it comes to your data. Okay, so I'm about to do this example for our Disney stuff. What are the axes of my prediction plots that I've been showing? Okay, running time is in the units of what? Minutes. And then rating is a unit list, but it's from 1 to 10. I think, yeah. Well, yeah, I took some of it out, but it's like 2 to 8, whereas minutes can be like 30 to like 300 or something, or 200, right? So the scale matters. So you want to normalize all the data that you pass into here. Otherwise, the runtime will totally dominate, or sorry, the ratings will totally dominate over runtime because the distances will look a lot closer, right? Because it'll say, so for example, if I were literally to use that exact data set, things vertically would make a bigger difference than things horizontally. So if you did this, if I did a point here and you did k equals 5, then if this was runtime and this was rating, unscaled, would this be red or blue? This would end up being blue because the closest points to this would be this, 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 and this, because the distance from here to here is like 4 to 7, whereas the distance from here to here is like, I don't know, 180 to like 210, right? So the model will think these are closer than these. Does that make sense? Yeah.
So you were saying if the unit on the x-axis was hours, like you'd probably have different results.
Yeah, yeah. That's why we have to normalize the data. Yeah.
I get it when you use numbers, but what happens if you put on categorical variables?
You can't do k-means on.
Categories at all.
Yeah, because there's no concept of distance between categories. It has to be continuous. Any other questions? Okay, so let's take a look at this example. So yeah, I'm moving a little bit faster through here, so I'm just I'll leave this as reference for you guys. This is normalizing the data to scale everything so that when I do the distances, it's all comparable. And then we use a library called class that runs a KNN. KNN is k nearest neighbors model. Okay, so let's see what this looks like for k equals 5. So I'm not doing cross-validation right now. I am simply just running based off of, I'm just running it based on the k equals 5. Okay, so you can get a lot more non-linearity with this, right? And so Okay, maybe I'll do it with the cursor. So basically what it's saying is let's pick an arbitrary point. So let's say I pick a point right here. Everyone see the cursor moving around? Yeah. So right around there. Question is, who are my 5 closest neighbors, right? So that would be 1, 2, 3, 4, 5. So there's 4 red and 1 blue. Therefore, I am red. Okay. If I am right here, right, who are my 5 nearest neighbors? It's probably 1, 2, 3, 4, 5. So 3 green, 1 red, 1 blue. Therefore, I'm green, and so on, right? So purple, if I'm like right here, 1, 2, 3, 4, 5 maybe. So 3 purple and 2 green. So you can extend that logic to classify basically any point in this map. Okay? And as you can see again here, is not confined to having linear boundaries as we are in the MNL or the LDA model. If you were to do, if I did a cross-validation and I figured out what the best K was, how do you think this model would compare from a prediction standpoint against MNL and LDA? What do you guys think? Better or worse? So if I had another test set of data, or if I pulled out some data from this and were to test it against the model, right? If I had those, the linear version versus this version, which one do you think will provide more accurate predictions? Yeah.
I think this one.
Yeah. So generally speaking, when you introduce flexibility into the model and allow the model complexity to figure itself out based on the basis of cross-validation, you're usually going to be achieving better results from a prediction standpoint. And that's going to touch on this concept we're going to move on to, which is this idea of like prediction versus, well, what are the benefits of having the MNL model? Well, we get like coefficients and we can actually understand how relationships will relate to outcomes in direct relationship terms. Whereas in this model, we can't say anything about how really runtime relates at all to our outcome, right? And so this is the kind of allusion to the dividing line between doing predictive-based models and more causal-based models, which we're gonna, get into a lot more today. Yeah.
I'm not sure if the question is appropriate for this lecture, but one of the things that I'm trying to figure out is why do we have the R color in the background this time and we didn't have it last time?
Yeah. So in the models that we ran, MNL and LDA, because they only have they're only allowed to have essentially linear dividing boundaries between our decision points. It just so happens that the R rating never is the most prominent outcome. That's all. And in this case, it's just saying that it just so happens that there are points in the space where the majority of points are purple, the neighbors. Yeah. And just note, this was an arbitrarily chosen K. We can Okay, this one's gonna take a little second to populate, but we can run the same model for k equals 1, k equals 2, k equals 3, all the way up to however many points there are in the entire model. And as I was saying, the choice of the k, the sort of most robust way of doing it is with cross-validation, which the package actually will let you, it'll kind of do it for you automatically. But just to give you a sense of kind of what happens is I vary the k whenever it decides to render. So this is going to be a bunch of plots looking at k equals 1 through k equals 10, just so that you can see what that looks like. One day. I should have ran this before while I was talking. Okay, here we go. Yeah, so it looks a little messy, right? But you can see, for example, at k equals 1, you kind of have the most territories, right? Because literally every single point is going to have some boundary area around it that's going to be defined as, that as the space of that point. And then as you increase in your number of k's, those boundary sizes will start to decrease and conglomerate with each other until eventually you only have one color, which is just whatever the most popular, whichever class has the most data point representations, right? But you can see at like k equals 1, like in the bottom right, it's all red, right? But eventually ends up becoming, green or blue, right? And as the k gets bigger and bigger, the purple spaces are going to decrease because those generally are just the least in prevalence. Okay? Yeah, so this is kind of like a non-parametric or a semi-parametric approach to classification. You don't get any information about the relationship between variables, but it can do pretty well in terms of predicting classes if that is your end goal. Okay? Any other questions? All right. So let's move on. So a lot of what I've been talking about in terms of the way that we measure strength of our models, right, with mean squared error as a metric, and then doing validation based on out-of-sample predictions, a lot of that way of thinking is related to this idea that we use the models for predictive purposes. In other words, I want a model that will give me the best Y predictions as possible. And we've been thinking that way and calibrating some of our simple models. And we're going to continue down that path as we get more complex models. But before kind of forking that way, there are a whole series of approaches and a way of thinking that wants to retain the kind of simplicity of some of these earlier models that we're talking about, like linear regression models, because of its interpretability, specifically in this idea of understanding like relationships between variables as opposed to predicting outcomes. And so we're going to get into that world today. And that is kind of this idea that we use these types of tools in order to determine causality. Okay, and so I'm sure you guys have heard of this expression that like correlation. Hold on. So correlation does not equal causation. Okay, so what is the difference? So correlation is the relationship between variables, and causation is how one event is the result of the occurrence of the other event. So we haven't really done any causal inference in this class so far. And causality can be a difficult thing to prove. And we're going to walk through a number of examples to kind of help demonstrate this. In general, the idea that you can demonstrate causation is through something known as identification. Okay, so this is kind of the process. So this is the process of figuring out what part of the variation in your data answers your research question. Okay. So a lot of what I'm going to talk about today comes from this one book, which I think I've linked it on Canvas. It's called The Effect by Nick Huntington Klein. It's an introduction to research design and causality. I think it's what happened here? Okay, are we still going? Yeah. All right. So this is, I think a really accessible textbook that does a great job at covering kind of causality identification in general and the tools that you use to do this type of analysis. So if folks are more interested in the like causal side of things, I would highly recommend using that as a resource. So there's an example that they have in this book that I really like. Okay, so we'll kind of talk through this. So you've got this house. Okay, forgive my like terrible drawing. Okay, and you've got this family living there with a dog, Abel and Annie. And one day they wake up and they find that their dog is outside rolling in the grass. And so Abel says, "Oh dang, like how did this dog get out? We need to make sure dog isn't able to go outside while we're sleeping. So that night, he has this little doggy door, and so he latches it shut. And he says, okay, I bet it'll be fine now. And so go to sleep that night, wake up the next day, dog is outside rolling in the grass. And he says, oh, dang it, like apparently he wasn't going through this door. So let me make sure to latch the back door. So he closes the back door and he locks it, and lo and behold, the next morning, the dog is outside rolling in the grass again. And he thinks to himself, oh, maybe he's going through one of the windows upstairs. And so he closes the blinds. And so we've got our window here, and we close our blinds. Okay, and so again, next morning, wakes up, dog is outside rolling in the grass again. So next night, he blocks the air vent. He locks and latches every door. He closes every window. He boards up the chimney. He plugs the drain in the bathtub. Everything you can think of. And next morning, dog is outside rolling around in the grass. And so he's like super frustrated, and he says to Annie, like, I don't understand. I've closed everything. How is this dog making it outside? And then Annie says, oh, I open the basement window every night to let in air. I bet he's getting out that way. And so the next day, they leave everything open except they close the basement window. And then the next morning, the dog is inside the house. Okay, and so this is a sort of classic example of sort of in an analogy, like closing avenues of escape, right? And by doing that, you are trying to identify what is the mechanism the dog uses to escape the house by controlling for all possible explanations. Okay. And so, yeah. By closing avenues of escape, we are identifying the answer by controlling every possible explanation. Okay, and here is an important principle, is that can we ever really control for every possible explanation? No, right? And so you have to think about what's kind of plausible. And this is where a lot of the art of deciding and controlling things comes into play, right? Like, you don't know, the dog could have been teleporting outside of the house. It could have, maybe the dog can walk through walls, right? You can't control for that. And so when we think about sort of plausibility and kind of the real world, you may not have to explain away a dog's ability to teleport or a dog's ability to walk through walls, but there may be other things, right? And so you can never truly accommodate every possible explanation, and so you have to be comfortable with kind of defending your choices. And like oftentimes if you go to a more like econ based, identification talk, most of the time they're not necessarily talking about the specific results. They're like spending a lot of time defending their decisions on variable choices and that sort of thing. So, just one thing to be aware of. So we're going to, we will learn statistical tools for closing doors. But this is just part of the puzzle. So inherently, assumptions are going to be necessary for what we call the data generating process, which is the actual relationship between outcome and your sort of hypothesis. Okay, any questions about this so far? Great. So we're going to think about visual representations of relationships. This is like a very common way that people think about things in the sort of causal inference world. And so we use something called causal diagrams. And this is a graphical representation of causal relationships. So you have variables represented by nodes, and you have causal relationships represented by an arrow from the caused variable. Oh, sorry, from the cause variable to the caused variable. Okay, so x going to y. Okay, this is a simple example of a causal diagram where I am basically saying that changes in x leads directly to cause a change in y. Can anyone think of any examples of this? No ideas at all? Something leading to something else? Yeah.
Hunger leading to eating food.
Okay, great. Hunger leading to eating food. So we can say hunger going to eating. Great. We can have other variables that are in the diagram. So we can think of a whole class of variables called u. This is known as an unobserved variable, right? And so this could be something that affects your hunger, which may then cause you to eat. And so, can anyone think of an example of this? What's something that would make you hungry? Yeah.
Just describing something, like your brain just starts salivating or doing something, like if you're very descriptive about a specific food.
Okay, sure.
Or like looking at a photo,
Yeah.
or seeing someone eat something.
Yes. Okay, great. These are all great examples. And actually particularly so in the sense that, like, okay, eating you can quantify, and you could quantify like some amount, right? By like weight or calories or something. Hunger, maybe you can ask people to say how hungry they are on a scale of 1 to 10. But a lot of these other things maybe might contribute to hunger. Maybe they could even contribute to eating even if you aren't hungry, right? You see something that looks really tasty, you're not hungry, and you still eat it. And so, yeah. And so generally speaking, even if it doesn't affect the why completely, we still want to include u in the graph. And the trick with this, so in this particular example, you see something really tasty and so you eat it. How much of that is you seeing that tasty thing and wanting to eat it versus you being hungry and you wanting to eat it, right? And so if I were particularly interested in this effect, then I now have a confounding variable, something that's confounding that effect if this relationship indeed exists, right? And that is one of the most difficult and classic problems to deal with in trying to determine causality, is that you have to somehow separate out this idea that, looking at this tasty picture of food made me eat something, but me being hungry also made me eat something. So how much of it was that picture and how much of it was my hunger? We need to figure out ways of dealing with this. So that's one common issue. Let me give an example of another one. Let's say I have, I decide to do some kind of research project, and I want to look at whether or not people who eat ice cream, if there is something related between shorts and ice cream. And so I go out and I observe that when people are wearing shorts, we see a lot more people eating ice cream, right? And so I come to the conclusion that wearing shorts makes you want to eat ice cream. Right? And you can see that in the data like very clearly, right? I can see on days there's a bunch of people wearing long jeans, no one's eating ice cream, and then on days where I see lots of people in shorts, they're all eating ice cream. Therefore, people eating ice cream means, or people wearing shorts causes them to eat ice cream. But in fact, this is probably not the case, right? So what is explaining this? Yeah.
Warm weather.
Yeah, warm weather. So we have, maybe not this, we may have some kind of unobserved variable which is doing something like this. And so this would be an example of a latent variable causing both effects. So this would be warm weather causing people to eat more ice cream and also causing them to wear shorts. So people are more likely to wear shorts on days they eat ice cream, but it doesn't mean that they cause each other in any way. So we need balance. So if you omit too little, many things may end up looking causal. And if you omit too much, you might miss the causal variable and get identification wrong. So you want to develop a defensible hypothesis and set of assumptions. Okay? Yeah.
If you're studying a field where it's like difficult to like identify a potential unobserved variable, are there tests you can run on your data set to see if there are unobserved variables?
Not really, in the sense that like if it's unobserved, you don't know what could potentially be affecting your data, which is why it's more kind of assumption driven and hypothesis driven than I would say specifically driven by some kind of like quantitative like test that you could do. So there are tests to determine how good identification could be, for example, and we may talk about some examples of that. But a lot of the strategies are having to do with like, I think the most effective ones are like drawing these like causal diagrams and being able to really defend them well. And right now, what I've done here is kind of introduce the problem. And what we're going to do now is think about, in theory, some of the ways that you can deal with these types of problems. And then either today or next class, we'll look at some tools that will be able to implement the things that we're kind of talking about. Okay, so let me talk about one more potential thing to worry about. Yeah, okay. So let's look at something like this. This is both an avenue to be a problem, but also we'll see how this could help in some ways. So we have x going to y, and then we have something known as a moderator variable. Okay, so z modifies the effect of x on y, but is not causally related. So this is one thing to watch out for, and a potential thing that could be important to control for. So you have some kind of variable that you're interested in studying, and it leads to some kind of outcome in y, but there's this moderator variable that can also have an influence on the outcome in ways that are unrelated to the actual effect of the thing that you are, or that are unrelated to the actual intervention measure that you might be trying to measure the causal influence of. Can anyone think of an example of this? This one's a little trickier, yeah.
I'm not sure if this is right, but using x as hunger, y as food eaten, z could be adherence to a diet, I guess, or food availability.
Yeah, let's see.
Blood sugar level.
Yep, I think that works. So hunger, extra points for using a example we were just talking about. So hunger, eating, and then you would have so like diet choice or something like that. It doesn't affect your hunger, but it affects how much you eat. Okay, maybe there is something related here that you could argue, so that might make it like if we were in a talk, I would ask you to defend that, right? But yeah, but generally I think that's the right idea. Yeah.
Or like if the MU was like handing out free burgers or something like that. Would that be a good like moderator variable where it's not based on if you're hungry, but
Yes. And it affects your eating. Yeah, if you partake, yes. I think that would be so. Yeah, these are good examples. The classic example that I see talked about is something like this. So you have a fertility drug, which affects your chance of getting pregnant. Does anyone think of a good moderator variable for this? How about having a uterus? So, fertility drug probably isn't going to work great if you're a guy. Well, yeah, you know what I mean. You're taking a fertility drug is not going to get any guy pregnant, right? But the moderating variable being you being a female is going to have a pretty big effect there, right? And so this is like the classic example of a really, really strong moderator variable. Yeah.
Would age be, I don't know, like, I'm
Yeah.
having a hard
Yes.
time, can it be like a static thing, like your age only changes every year, but.
Yeah, yeah. No, but if I were to, so the idea is like, okay. If I have, so, pregnant, fertility drug, okay, and you have something like 1, 1, 0, 1, 0, 1, 1, and then you have something like, 1, 1, 1, 1, 1. Okay. If I were to just run this in a regression, this would tell me something about the efficacy of this like fertility drug, right? But if I were to add a control for uterus, and it would be something like this. Okay, I have to be careful here. We'll do something like this. Right? That would now, and I include this as a control, that would now change the efficacy of my fertility drug, even though these have nothing to do with each other. Right? So, onto your question, if I have age, right? So let's X this guy out. So if I have age, that could be like age where the range in which you can viably become pregnant, right? So whatever range that is, and then post menopause, right? That would act kind of like what the uterus variable is doing, and that again wouldn't be related to the fertility drug part of it directly. Yeah. So yes. long story short, yes. If I were to just say, so 1 being of an age that you can get pregnant, and 0 being an age you can't get pregnant, you could do, right, the same type of thing, and it would look similar. And including this is essentially modifying the behavior of your fertility drug. Does that make sense to everyone? Right, because essentially, if you were giving the fertility drug to a whole population of people and half of them were male, and you looked at the numbers, you're like, oh, this fertility drug doesn't work very well because like only a third of the population is getting pregnant, but you forgetting the fact that half the population can't get pregnant, right, is an issue. And so moderator variable can be an important way to capture effects like this. Yeah.
In this example, people can choose to take fertility drugs because of age to enhance their chances of pregnancy.
Yeah. But it's not about the choice, right? It's about whether or not the fertility drug directly causes you to become pregnant or not. Yeah. Okay. All right. So, let's talk about some general rules. So I think I've covered some of the most common types of issues that you run into when we think about identification. We're going to look at an example, but before that, wanted to give some pointers for actually putting the diagrams together. So, simplifying your diagrams. So 1, if it is unimportant, if arrows are tiny / unimportant, you can probably remove. Two, redundant. If there are variables that have the same arrows coming in / going out, then just combine them. Three, mediators. If one variable is only on the graph as a way for one variable to affect another. So this might be like A going to B going to C, then remove it. So for mediators, just to kind of clarify really quickly, I'll leave this so that we can see. If I have something like A, B, C, and I'm interested in the effect of A on C, I can, in this particular case, just get rid of it. But if there are any other paths that are happening, if I am going around it, or if B is going to something else, in this case, you cannot remove this. It's only if it's purely a mediator variable. Okay. Irrelevance. So if it's part of the data generating process, but not relevant to the research question, remove it. And then the last thing, so diagrams must be acyclic. That means no loops. Okay. All right, any questions? So let's put this all together and let's look at an example, and then we're going to try and break it down and think about the sort of principle behind all of this. All right, so we are going to look at this diagram. We've got our research question where we are thinking about how wine can influence your lifespan. And there's other things that we want to think about including here. So we have drugs. So lifespan, so you drink wine, that may affect your lifespan in some ways. Maybe you also take drugs that could affect your lifespan in some way. Maybe there's a relationship, right, between people who drink a lot of wine and who do a lot of drugs. Let's say we have income, which affects how much wine you can drink, and income in itself may have some influence on lifespan. And then we have health. And let's say health affects wine and lifespan. And of course, let's not forget, we have our unobserved variable. And let's say that affects our income and health. Okay. So this particular diagram, as right or wrong as it is, let's suppose we take this as kind of ground truth, okay? Let's suppose you have a hypothesis, you figure out the relationships, and you are able to defend essentially the diagram and the relationships that are depicted in this diagram. We are interested in specifically wine as our treatment and lifespan as our outcome. And so to do this, we have to find all paths. So we need to find all the treatment and we need to find all the ways, treatment and outcome variables could be related. Right, so treatment and outcome. So there's actually a procedure for doing this. And we are going to write out this procedure, and then we're just going to follow it to figure out what all the paths are. So start at treatment variable. Follow one of the arrows in and out of the treatment. To find another variable. Follow one of the arrows in or out of that variable. obviously not going back to the one that you started with. So 4. Repeat 3 until you find the outcome. And that would be a path. Or a variable already visited, which would be a loop, not a path. And then every time you find a path or loop, back up 1 and try a different arrow. Okay. So, let's find all the paths together. Who can help me find a path from wine to lifespan? The earlier you go, the easier it'll be. Yeah. Wine to drugs to lifespan. Great. Wine, drugs, lifespan. Okay. Who else? Yes.
Wine to lifespan directly?
Wine to lifespan. You got the easiest one. Okay. Any other paths? No? Really? Remember, you can go the other way too, right? It's in or out. So you could say from instead of to, yeah?
So we could go wine and lifespan too.
Wine, health, lifespan. So wine from health to lifespan. Okay? That opens up the doors, right? What else do we got? You guys have gotten 3 out of the 7. Yeah. Oh yeah, sure. Wine, income, lifespan. Okay, 3 more.
You do like wine from income, from unobserved variable to health to lifespan.
Perfect. Wine, income, U1, health, lifespan. Okay, got 2 more. Yes.
Wine from income to lifespan via drugs.
Wine, okay. Wine from income via drugs. There's no link between, is that what you said? There's no link from drugs to income. Your starting point is wine and you always end up with lifespan.
Yeah, so from income, wine, drugs, lifespan.
But your starting point is not wine, right? You always, step 1, you always have to start at the treatment variable. So, not quite a path, right? So if I were to draw what you were saying, income, wine, drugs, lifespan,
Yeah.
there's no way to orient this to be at the beginning because there's no connection between these two that don't go through your treatment or your outcome variable, right? Does that make sense? Yeah. Yes.
Line from health from U1 to income to lifetime.
Perfect. Yes. So wine, health, U1, income, income to lifespan. Okay, we've got that one. Oh, 6. Oh, there's 6, not 7. Sorry. That's all of them. Okay. So these are all the paths that you can derive from this diagram where we're starting at our treatment and ending at our outcome. All of these paths represents essentially a plausible story, right? And so if I wanted to specifically identify the effect of wine on lifespan, I have to close all of my other paths. Otherwise, one of those paths could be explaining this this effect, right? So I drink some amount of wine and that affects my lifespan, and I say, oh, based on the amount of wine that I drank, I can see that it affects lifespan in this way. But what if it was actually the drugs that was affecting your lifespan, and the amount of wine that you drank was influencing the amount of drugs that you were taking, and therefore that effect wasn't real, it was really about the drugs. So instead, let's say we control for drugs, right, in some way, right? So putting aside the actual how we actually do it, right? Let's control for drugs in some way, and now I go back to that story. Well, now I've controlled for those drugs that was maybe explaining that change in lifespan, and now I can say the amount of wine that I'm drinking is affecting my lifespan. But wait, actually, whether you have good health or bad health is actually affecting your lifespan, and that affects how much wine that you were drinking. So it only looked like it was the wine, but really it was the health, right? And so you have to control for this. So the idea is when you build these diagrams, it helps you understand what is necessary, like not the spam call. It helps you understand what's actually necessary to control for when you want to determine causality, when you want to do this identification. And ultimately, we'll figure out the tools that'll let us do these controls, but prior to that, you need to build up this kind of framework to be able to defend the fact that my choice in controlling for certain variables in certain ways is essentially accommodating all these possible paths. Okay. Does that make sense? Everyone? Good? Let's talk about the path types. And this is going to start getting us closer to how we think about closing paths. So, a good path. This is a path that relates to your research question. or it's a path you are trying to identify. We have bad paths. This is a path unrelated to your research question. A front door path is a path where all arrows point away from treatment. And then we have a backdoor path. This is a path where at least one arrow points towards treatment. Okay, if I were to go back to here, okay, 1, 2, 3, 4, 5, 5, 6 is one front door, back door. Front door. Everything points out of the treatment towards outcome. 2, front door, back door. Front door. 3, back door, right, because something goes into the treatment. 4, back door. 5, back door. 6. Right, so we have 4 backdoor paths and 2 front door paths. Okay. An open path. This is a path in which there is variation in all variables along a path. And I'm going to put in parentheses here. We'll talk about this in a second. And no variation in any colliders on the path. A closed path is the opposite. A path in which there is at least one variable with no variation, or a collider with variation. So imagine really quick, we go wine, drugs, lifespan. Okay. If you have a bunch of variation in wine, a bunch of variation in drugs, and some variation in lifespan, I don't know actually if it's the wine or drugs that's leading to the change in lifespan. But if you have wine going to drugs, and the amount of drugs is, like, let's say the same between 2 different people, but you observe variation in the wine and lifespan, then then essentially controlling for that without having that variation, you can now attribute the effect to wine because there's no variation in that closed path, right? Because there's this. So you've closed this path because you've eliminated the variation. I have parentheses here. In an open path, you want variation. In a closed path, you don't want variation, with the exception of collider variables. What is a collider variable? Collider, this is a variable along a path if both arrows on either side of it point at it. So an example of this would be, say we have our treatment. We have A, B, C outcome. This is the collider. Okay, you have two arrows going into it on each side. And importantly, closed by default. If you control for the collider, the path opens unless you control for another variable in the path. Okay? So in this particular, well, we don't have a collider in our particular example, but for colliders in general, actually, they close the paths naturally by themselves. If you control for the collider, you actually end up opening the path. And so this can be difficult in practice to identify, but it's also one of the reasons why figuring out your causal diagram is really important, because sometimes you might have like a collider variable and people just like throw variables into their model and they're like, oh, I'm controlling for all this stuff, when really you introduce this issue where now you've opened up a path and you now have the possibility that there's something else that's influencing your outcome besides your treatment. Okay? Yeah?
Is it possible to have arrows pointing away from your outcome?
Yes, but we would generally consider that to be a bad path, in which case it's like a irrelevant type of thing where you don't really care about it unless it's influencing something else. Although generally speaking, you wouldn't set it up that way because it would be acyclic. So then you would have loops. So generally, you wouldn't be including things like that in your diagram. Yeah. Okay. Any other questions? Okay. So most of the stuff that we're talking about today is, trying to set you up for success so that when you want to address causal-based problems, that the sort of foundation of how you approach it comes from this framework, right? We want to be able to set up good causal diagrams, defensible causal diagrams, before you take the step of like implementing the tools that are going to like close paths and that sort of thing. So we'll end here for today, and then next class we will introduce a bunch of different ways that people think about essentially closing paths and allowing you to determine causality. Okay? Great. That's it for today.